Problem. Okay. Can you guys start on question 1, please? Question 1. And
Sorry?
Your friends?
They go to different schools.
you've done quiz 9, you can give it to me now. I will mark it and send it to you later today. You guys have done quiz 9. Thank you. Anyone else? That's done quiz 9. Thank you. Thank you, Mom. Thank you. We are doing question 1. We are doing question 1. Yeah. All right, guys. All right. Can you listen, please? So, question 1, the confidence interval we are looking at is p hat minus z. I mean, in my notation, there's a conflict of not in the handwritten notes. I use z1 minus alpha by 2, right? But that's the same as the z alpha by 2 in the printed notes. I'm sorry for the confusion, but I'll try to change it next year. But it's too late this year. But anyway, that shouldn't be a problem for the exam. Alright, this is the confidence interval we have for proportion. Now for part 1, we are looking at what is the width. What is the width of the confidence interval? I mean, the width is obvious, right? The width is equal to 2 times this, right, which is proportional to the standard error. So part 1 is kind of trivial. Okay. Part 2 is to sketch the graph of p times 1 minus p. And this is where your calculus comes in. You have the function v of p equal to p times 1 minus p. P between 0 and 1. Now, how would you plot this function, guys? I'm sure you did plenty of questions like this in your calculus and vectors. The first thing is that you just need to choose, the first thing is that you need to just choose 2 points. So v at 0 is equal to 0, v at 1 is equal to 0, and v prime of p is 1 minus 2p, right? Okay, which is, and this is this is equal to when it's a positive number if p is less than a half, and 0 if p is equal to half, and is a negative number if p is greater than a half. Can you see that, guys? The first order derivative is positive if p is less than a half, 0 if p equal to half, and less than 0 if p is greater than a half. So what it says is that it's it's an increasing function. It's an increasing function when p is less than half, and 0 when p is half, all right, and decreasing function when p is greater than half. Now we know that v at half is equal to a quarter, so the function will look like this. You should plot it. I'm not very good in drawing, as you all know. It will be this will the graph will look like this. It will be 0. It will be 0 at 0, and it will be 0 at 1, and it will reach the maximum value when p equal to half, right? Do you see how I got this? And part 3 we already done it, because to show that this function is maximized at p equal to half, all you have to do is do the second order derivative, which is minus 2, which is negative, right? So hence right, that's part 3. Part 4, hence find an upper bound for the width of the 95% confidence interval when n equal to 1000. So that's not difficult, because when n equal to 1000 and the width is going to be 2 times alpha is 1 minus 100 times 1 minus alpha is 95%. So alpha is, what would it be? I'm trying to figure out in my head. And somebody tell me what would alpha be if 100 times 1 minus alpha is 95? 0. 0. Are you sure? 0.05, yeah. So that would be z 1 minus alpha by 2 will be 0.975 times p times 1 minus p divided by n is 1000, right? Now upper bound on, because this function is less than or equal to half, this would be less than or equal to 2 times so less than or equal to quarter. I mean, it will be, this is the answer to it. Do you follow what I've done, guys? Well, because the confidence interval is 95%, this becomes 0.975, right? That's because you should go back a few steps earlier. I don't think you saw it here. Right, 1 minus alpha by 2, right? When alpha becomes 0.975, and our n is 1000, so this is 1000, and we know from this graph that p times 1 minus p is less than or equal to quarter, so this must be bounded by this. Now it's not really difficult. Can you do question 2? Question 2. Please. sign the attendance sheet, please? Is everybody signed? Attendance sheet. To do question 2, you will need these formulas. You remember these? Sorry, let me remove this. Do you remember these? This is a summary of formulas when we did last week. Summary of formulas for the difference in population means when the variances are known, when the variances are unknown but equal, and the variances are unknown and not equal. So these are the. So you need to use one of these three, or at least some of these three formulas to do question 2. You may recall these formulas from last week lecture notes, or don't you? Yeah. So just try to use this. Yes. Thank you, sir. So anybody who hasn't signed? You have some. Yes, okay. Oh, space 9. Come on, you should have thought about it during the weekend. It's too late now.
I did think about it.
I gave you a hint on last Monday. If you look at the notes.
Yeah, I looked at it. Can you keep the number here?
Yes, okay. Oh yeah, there's a complicated formula I gave in the notes. But I haven't mentioned it. It could take half a page.
Oh, great. Okay. I'll have to check out those.
I think it's in the notes. But I don't think you need to use that for this question.
Can we see that?
Only the first two.
Okay.
Yeah.
Yes.
Sorry. The table, yeah. There must be still here. So it's just a matter of using one of these formulas. So this is the formula when the population variances are known, and this is the formula to use when the population variances are unknown but equal, and this is the formula to use when the population variances are unknown and not equal. Yeah. I mean, I talked about it last week, you may recall. But this is not going to be examinable for the final exam, but at least because we did this last week, I just want to give you an example, right? I hope you understand. But this will not come in the final exam in May or June of this year. Right. So you have a random sample of 150 bulbs from brand A. So yeah. So for the first part of the question, for the first part of question 2, let me try to figure out where the answers are. So I don't have the, I won't be able to do without. Okay. All right, here we are. For the first part of question 2, what we have is M is 150, and X bar is 1386, and the sample standard deviation, which is you probably remember what I mean. The sample standard deviation is simply this. Right, and this is equal to 114. All right. Now, then you're given that n equal to 200. Y bar is equal to 1218. And the sample standard deviation, which is this is the sample standard deviation is equal to 98, right? Now the question is to find the confidence interval, 95% confidence interval for the two cases. I mean, for the first case, it's kind of complicated because you need to use the it's kind of complicated because you need to use the formula. Where am I? You need to use the third formula, which is you need to use this formula here, where A is a complicated it's a function that I mentioned in the lectures, but it's pretty complicated. So I will skip part 1. I will move on to part 2. In the case of part 2, that is in the case assuming that the variances are equal, right? In this case, the confidence interval will be X bar, which is minus y bar, which is minus or plus t. M plus n minus 2 is going to be 350, so 348. Because it's 95% confidence interval, you have 0.975, right? And then you need to multiply this by this expression here, which is sum of xi minus x bar squared, which is already given. I will just write it down without actually simplifying it. I mean, I'm sure you can, if you have a calculator, you can do it. All right, this is what you need to work out. All right, this is the confidence interval you need to work out, and each of these things is given to you, right? You are given the sum of xi minus x bar squared. You are given this. You are given m, and you are given n. So all you have to do is just sub all this in, sub this in, and work it out, right? If you have a calculator, I'm sure you can do it. So that's question 2. Now, okay, and well, maybe I can also do part 1, which I skipped. For part 1, it will look like this: x bar minus y bar, which is this, minus or plus t a 0.975. A is something that you need to work out using the formula I gave you in the notes, right? And multiplied by this nasty expression here, which is alright. I mean, you know, sorry, this is n minus 1. You know what each of these guys is. You know the sum of xi minus x bar squared. You know this. You know m, and you know n. So you just sub it. You sub things in, and you compute it. That's all you have to do, right? For the a here, you will need to use the formula. It's a huge expression I gave in the notes, in the handwritten notes. Yeah. Okay. All right. Can you do question 3, please? Now, question 3. Question 3, you don't need formulas. You just need to show that the estimators are unbiased, and you need to obtain an expression for the variance of mu hat, and then take the limit as n and n approach infinity. Are you guys okay? Alright guys. Now you have x1 to xn, right? IID normal with parameters mu and sigma square. Now, what does this mean? It means that x bar, the sample mean. Do you guys remember the formula I mentioned in the class? I mentioned this several times. X bar has a normal distribution with parameters mu and sigma squared divided by n. Okay? And similarly, you have y1 to ym IID with normal mu and sigma squared. So this implies that y bar, the mean of the y's, has a normal distribution with parameters mu and sigma squared divided by n. Right? And we need to show that we have mu hat. Mu hat is defined as n x bar plus m y bar divided by n plus m. Alright, we need to show that this estimator is unbiased. Now, do you guys remember how to show that an estimator is unbiased? I mean, I did 10 examples on this in the lectures. So all you have to do is you need to show that the bias of mu hat equal to 0, right? So which is the same as the bias, the expectation of Yeah, this is the definition of bias, you recall. So this becomes okay. Now we know that x bar and y bar have this and this distribution and this distribution. So this is right. So this is clearly 0, right? Hence are you guys with me? I mean, we did many questions on bias, so you should know this pretty well by now. Yeah? Yes? Oh, come on, guys. Are you not familiar with this? Right? And the next thing is sigma hat squared, or sigma squared hat is given as n minus 1 sx squared. Is it n or m? Yeah, n minus 1 sy squared. Sy squared is a sample, sx squared is a sample variance for the first sample, and sy squared is a sample variance for the second sample. Okay. Now you can write this. I mean, all of you know, I assume that you know the formula for the sample variance, right? So this will be right, this is equal to this. Do you see why? Because of the definition of sample variance, right? Right, now we need to show that this estimator is unbiased too, right? So we need to take the bias of this, which is the expectation of this, right, plus the expectation of right, okay, minus sigma squared, right? Now, do you guys recall this? Do you know some property of this summation here? I mentioned in the lectures, guys. What distribution does this have? Huh? Do you guys, you should remember, because I mentioned this several times in the class. Do you know something about this? Something about this and something about this. You don't recall? Come on, guys. Alright, let me write it down if you don't remember. This is equal to the expectation of sigma squared times the chi-squared variable with n minus 1 degree of freedom. Yeah? And the second term is the expectation of sigma squared times the chi-squared variable with n minus 1 degree of freedom. Right? Right, and then you subtract sigma squared. Do you remember this? This is one of the properties I mentioned in the class. If you don't remember, please go back and look at the scan notes, please. It's also in the list of formulas you need to remember for the final exam. This formula here, this from this to this, this to this. Alright? Now, so sigma squared you can pull out. Now, the expectation of a chi-squared n minus 1 is, do you remember, is n minus 1. And the expectation of chi-squared n minus 1 is m minus 1. And this is obviously 0, right? So hence, hence it's unbiased. Alright, the next, so that's part 1 of question 3. Now to do part 2 is to find the variance of mu hat. So this is part 1. Now I'm going to do part 2. Is this all clear, by the way? Yeah? Are you sure with this? Okay, now to do part 2, we want to find the variance of mu hat, which is the variance of, sorry, let me pull this out. Variance of variance of this, yeah? Now if you put, because these are all constants, this becomes right, this becomes this. Now, you know the variance of x bar because of the property I mentioned earlier, that is this one. X bar has this distribution and y bar has this. The variance of x bar is n squared multiplied by sigma squared divided by m. And similarly for this one. Okay, so what you get is sigma squared divided by n plus m, right? And this clearly approaches 0 as n approaches infinity and m approaches infinity. All right, are you guys okay? So that's question 3. When you do question 4 now, please. Question 4. I hope this is okay to all of you. If not, let me know. Question 4, you need to use the formulas. So put the formulas back on. Remember the formulas I mentioned. You need to use the formulas, this formula here. You will need to use this one here, the one in the bottom. This is the formula for the confidence interval for the difference in two proportions. I think question 4 is about that, I think, if I'm not mistaken. Question 4. Yeah, question 4 is about. Oh, is it? Oh no. No. Question 4 is not that. Well, for question 4, you need to use one of the first 3. Yeah, you just need to use one of these top 3 formulas for question 4. Yeah, one of the top 3.
Give me 2 minutes on the structural. Yeah, so just checking the before.
So I think you need to basically use the second formula for question 4. You just need to use the second of the 3 formulas to do question 4. I'm sure you can. So anybody else who wants to hand in question number 9? Question number 9, anybody else? I'll see you guys at 3 o'clock, okay? Make sure you come. don't know. Thank you, man. Thank you. There's no name or there's no idea.
I'm wondering if you don't get my homework.
No, I got your homework. I just did you know who this guy is.
So you send it to all students?
Yeah, send it to everyone.
Okay, then that's fine.
There's something about the R syntax,
Yeah.
about the full modus test. So in the syntax we write the name of the vector,
Yeah,
the distribution,
and
the
then
mean and the variance.
yeah,
And
you have to put this in parts in.
yeah, I did, and the result should be bigger than 0.05.
Yeah.
But the result I got was 2.2 e to the minus 16.
That means it's the normal distribution is not a good fit.
Yeah,
you
I
have
tried
to, you have to, you can try logistic.
It got 2.2 e to the minus 14.
Are you sure?
Yeah.
How did you fit the logistic? You had to first fit.
Yeah, I fitted over it and I think it did fit on the
No,
fourth test.
but you need to, logistic has two parameters.
Yeah.
Did you actually estimate them using fit test? You
Yeah,
have to estimate, you have to use fit test, right? And estimate the two parameters of the logistic. Oh. And then when you use case test, you need to put the two parameters here. They are not mean and varying, there will be some other values.
Yeah.
It will not be this and this, it will be some other number.
Okay.
It will be some other numbers.
The fit test showed me 4 pictures and it fitted the distribution over my data.
Yeah, I know, but that doesn't mean, I mean, the picture doesn't mean anything. You have to actually perform the case test. I mean, the picture may show you it's a good fit, but may not actually mean it's a good fit. You know what I'm saying?
Okay.
So to make sure it is a good fit, you need to perform the case test.